Today we're going to look at stepper motors. You might find a stepper motor in your scanner. This is from my scanner, which I destroyed when I got my all-in-one printer, and I took the stepper motor out. Some things to notice: 4 wires. There are 2 phases in the stepper, and there's a plus and minus for each phase. How do I know it's a stepping motor? Well, one simple test is to just feel it. And as you turn it, it feels like there's kind of grit or sand inside of there. So I know for sure that's a stepper motor. For instance, this is an industrial stepper motor, and being industrial, it says on the back with its nice label that it's a stepping motor. And again, I can turn that, and this time it feels like it's got very fine sand in it. This is 200 steps per revolution, so 200 very fine steps, and I can feel those. Well, how is that achieved? Well, that's what I'm going to show you using this demo and the lecture notes in a moment. If I just turn this, I can feel again, it feels like sand. I've got a magnet on there. So these are known as hybrid stepping motors because they have simple poles that are energized, plus or minus, usually 2 pairs or 2 sets of those, 4 wires, and there's a magnet inside. So with the magnet, you get that sandy effect, and so I know there's a magnet in there. This is a hybrid stepping motor. Well, how is it all done? We can go to the lecture notes up there, and what you can see very clearly there, pole 1, you can see on pole 1 that it's a simple winding plus and a dot around pole 1, but the pole itself has teeth on it, and the rotor in the middle has teeth on it. And very cleverly, the teeth from pole 1 to pole 3, for example, the teeth are aligned on pole 1, but misaligned on pole 3. Remember what we said. And these little teeth, in fact, are known as castellations. Each of those poles looks like a castle, and that's exactly why it's called a castellation. And this is your classic hybrid stepper motor, which is probably 99% of all stepper motors. Where does the magnet actually go? Well, we need to look on the picture on the right. You can see the magnet is in between the 2 wheels. There's 2 layers of the motor, and we split the rotor into 2 and put a magnet in between. The magnet is cross-hatched in that drawing. So you can see the flux comes through the pole, across the motor, and then down the other wheel back into the pole. So pole 1 and pole 2 are phase A, if you like. Pole 3 and pole 4 are phase B, and this is your structure of your motor. And subtly you can see that there's the teeth are shown in that right-hand drawing as well. The teeth are misaligned between the 2 wheels. Well, just to show that in a little more detail, what I've got here is a little demo I have made up. And this is what's called laminations. It's 2 very thin layers of metal. These can be stamped out, and they're stamped with an incredible level of accuracy, which is typical of stamping process, out of the thin metal, and you can see the castellations there, the poles around here. Now this has 8 poles, whereas the one up there had 4 poles, but there's still A and B, or A bar and B bar, just depending on the direction of the winding. So it's still a classic stepper motor. This, I think, gives you 400 steps per revolution, but I'd have to think about that a little bit more, count the number of teeth around there and so on. Well, that's the structure of it. Let's see how it works in detail. So we can put that on the overhead projector here, and we can see through it. Well, I'm going to pretend that my little bar magnet there, my geomag, is my excitation. So I put a current in the pole and I get a magnetic field, and that brings that set of teeth at A at the top into alignment. So in fact, expanded up as much as it is, you can see that these teeth are beautifully aligned. And these other ones are misaligned around here, B bar, A bar, B, and A down here is aligned as well. So in this case, it's the flux going in on both sides through the wheel and out 90 degrees out the other side of the wheel, as in the drawing in the lecture notes. So again, beautiful alignment down here. Well, how does it go around? Well, let's excite it with B bar. And you see you get a very small movement, and that's perfect for your laser printer or your scanner. And we can excite A, again a small movement, back to A, keep going around. So you can see we go around one revolution around here, and the middle wheel has not moved very much at all. In fact, we ought to check that, but there we go. You can check that in your own time. Bit of homework for you. How about that? But you see the motion around here, a gross motion of the excitation, gives us a very fine movement. And that's just what we want for a printer. Well, that's the basic theory, the basic structure. But you know what? Engineers like to do things more cleverly than that. So there's no reason, for example, why you shouldn't get another magnet, for example. Oops, whoa, that was good. I've lost my previous other magnet. And what happens if we put two on at one time? Well, we got a small movement, but it was smaller than the movement we had before. So let's take off the first magnet. Oh, small movement again. Take that, move that back, move it forward. Now that's known as half-stepping. So in fact, we've put magnets, or excitation as it's called, or current as it's a winding electromagnet, on on both windings at the same time in a particular direction, and we get a half step. And that allows us immediately, instead of just 200 or 400 steps per revolution, we can have 400 or 800. So we've instantly changed the number of steps that we can do. What's the drawback of that? Well, more current, because you're now exciting two windings, the motor will get hotter and may not be able to sustain that. But in many applications, the gain is better than the loss in heat or whatever. So we might want to do that. Well, as I say, engineers like to manipulate these things. So you can buy a chip now that drives the stepper motor, and instead of just having full on here and full on there, getting half steps, what we can do is we can put a little bit on one and a bit on the other and more on the other, and we can graduate it. So you can typically go with a classic chip, you can quite reliably go to about 8 steps between a pair of steps, 8 little mini steps. In fact, they're called micro steps between the normal steps, just by adjusting the level of the current. Again, this is easily done with a chip with the current feedback resistor and a sensor, and we can easily control that. And you can look that up on the internet, stepper motor drivers, you'll find that for yourselves. Micro stepping, and that again shows the strength that we can control more accurately. But you'll appreciate that that's not very symmetrical. The half step is symmetrical, the full step is totally symmetrical in terms of the motor, but anything in between, you're kind of chancing it a little bit. What other issues are there with stepper motors? Well, there is no position feedback on a stepper motor. That feels very sand-like. There's no position feedback on the stepper motor. That's one reason they're cheap. They give you accurate position without feedback, so that's very good. Well, sometimes it goes wrong. So your scanner likes to calibrate itself by going back to the end and starting afresh each time. So it's setting at 0 and hopefully counting its way all the way down without losing any steps. How might it lose a step? Well, one of the problems is as it goes from position to position, there's nothing to really stop it going over to another position, except I'm having to apply some force to it, some torque to it to make it do that. But it doesn't know. There's nothing in the motor to tell it hasn't done that. Well, what about when we're moving from step to step? What if there's a resonance in the load, a mechanical resonance? Well, let's see what happens. Let's see if I can show a little oscillation as the thing pulls in line. So I'm going to spin the rotor, and then hopefully you'll see it oscillate as it comes into line. Oh, didn't manage to spin it then yet. Not spinning it very well. There we go. I have to get my hand out of the way in time as well. There we go. Let's do that again. What you hopefully can see is a little shake as it pulls into line. It looks quite good, actually. It looks quite good, but you can imagine that under some conditions, as you move rapidly around here, you might hit a resonance, a mechanical resonance, and lose a step. And that's one reason why micro-stepping might be quite good. Not for accuracy, just to stop mechanical resonances. It's also one reason why you wouldn't find this sort of motor in applications where the load changes. So in a laser printer or a scanner or a knitting machine, the load is pretty constant. So we know exactly really what the load is, a piece of paper or the scanning head, and we have no fear of it losing steps, losing position. But in an industrial machine tool, machining pieces of steel, then this would not be appropriate because you wouldn't know the load changes. It might hit a resonance, it might overstep and go to the next one, as we tried to illustrate. Well, that's the modern stepper motor. There's other variations on that, but that covers the majority of stepper motors. Magnets are cheap, so hybrid stepper motors are the way forward.